So I'd like to thank everyone for coming today. Noah and I will be giving back-to-back talks on engineering and construction of genes to genomes, and this will give you kind of an introduction to synthetic biology. So to start off, it's actually been 25 years since we started the Human Genome Project, which was to sequence the human genome. We completed it 15 years ago, but the importance of this is that there is a significant amount of DNA sequence that suddenly became available to researchers, and this was a big driver, as you'll see, in synthetic biology. If you look at the NCBI database, so this is the government's database for having or holding base pairs, there's over 190 billion base pairs today of content that researchers can use. And while not the only driver, this is one of the primary drivers why we're talking a lot about synthetic biology. So what is synthetic biology? Synthetic biology is when researchers want to design and construct new genes, new tools, parts, devices, or systems, or they want to re-engineer, they want to reconfigure existing systems that are in place. And what researchers are finding is that if you do this, you can actually take those gene components, those pathways, or even genomes, and you can put those into host systems. These can be E. coli, these can be yeast, and create new entities. So these could be molecules that already exist, or they could be new molecules. And the applications are in biotherapeutics, they're new enzymes, they're in biofuels, they're in chemicals, they're in agriculture. So the application of these is pretty tremendous. So one of the things that is really holding us back in this space is there is a huge difference between our ability to now sequence or read DNA. So I talked about the Human Genome Project and what that meant. That meant the ability to actually read the DNA. We have, as an annual capacity, we can read 3 trillion base pairs of DNA content, but our ability to write or synthesize DNA is really compromised. We only have the ability to write about 1 billion base pairs. That represents about a 3,000 fold difference between those two. And so my company, Gen9, this was kind of our charge. We believe that we could use semiconductor technology that would allow us to develop a high throughput process for DNA synthesis to make very high quality DNA at an affordable price. So Gen9 was founded in 2009 by 3 visionaries in the field of fabrication, genetics, and bioengineering. So that was Joe Jacobson from MIT, George Church from Harvard, and Drew Endy, who's now at Stanford. And through the support of very generous investors, Draper Fisher Jurvetson, the Kraft Group, and Agilent Technologies. And we had commercial product in 2012. So this was DNA synthesis that we have been providing to researchers since that time. We're located in Cambridge, Massachusetts, and we have about a little over 50 people now. So in our process, if you look at from beginning to end what our process is, it is a high throughput DNA synthesis process. And I'll come back to that because this really distinguishes us from other DNA synthesis vendors. Why another DNA synthesis vendor? Because we don't have the ability to synthesize the DNA that's necessary to drive synthetic biology to where we need it to be. So when you look at this process, we start with a design component, the ability to synthesize oligonucleotides and assemble them, an error correction strategy that allows us to provide sequence verified molecules at the end. But the important point is all of this needs to be high throughput, and I'll stress that with a couple of examples. So today I'm going to focus primarily on the oligosynthesis component as well as the assembly component, because I think that that's a critical element for people to understand in DNA synthesis. So researchers come to us and they have a specific DNA sequence, and it could be hundreds, could be thousands, could be any number of lengths. And in our design strategy, we actually deconstruct that DNA so that we are able to put that into smaller oligo segments that then have built into them the design instructions for the assembly process. So why is this critical? It's critical because the next step is really to do the synthesis on a microarray chip. So microarray chip technology has been around for about 20 years. So this is an example that came out of Lee Hood's lab. The paper was published in 1996. And it shows that when you apply a substrate to a glass surface, you can create a hydrophobic surface that has a hydrophilic spot, essentially, in it, creating an effective well, a surface tension well, if you will. And that surface tension well has approximate diameters that can be anywhere from 30 microns to over 100 microns. And that gives us the ability to do massively parallel oligosynthesis. So what does the oligosynthesis look like? It uses the same phosphoramidite chemistry that's been developed and has been employed for over 30 years. You use the same strategy of deprotection, coupling, capping, and oxidation that are required, but that actual printers apply each of those amidites in subsequent rounds on the glass surface. So again, keep in mind that that glass surface is about 75 millimeters by 25 millimeters. And just to give you an orientation, each one of those chips can hold about 3 genomes worth of bacterial genome content, or approximately 50 million base pairs. So there's a significant amount of content that can be put onto each one of those chips. The problem, and why people hadn't done this more frequently, is that when you look at the overall chip, you have to make sure that you have good representation and good fidelity. The advancement in really chip printing for oligosynthesis has advanced so that the histogram that I show on the left-hand side shows that we have representation of all oligonucleotides on the chip. And then we have modest fidelity of the oligos on the chip as well. Modest fidelity means that we have about 1 error in every 200 base pairs. That's not very good for actually building gene content. And so we also have at Gen 9 a proprietary enzyme error correction strategy that we use. Our CEO likes to call it like a error correction for the read and write capabilities, so it'd be like a spell check. But the error correction strategy that we employ is enzymatic, and it gives us a best-in-class error rate, so that we've seen error rates of 1 in 40,000 base pairs. That's sufficiently large that allows us to create an industrialized process that extends that oligosynthesis length up to 10,000 base pairs very easily, and then ultimately allows us to sequence verify. So the process of doing the oligosynthesis has to be coupled with a high throughput assembly process. And one of our other founders, George Church, published a paper in 2010 that demonstrated the viability of using this strategy. So taking oligonucleotides from a microarray chip, he showed that in fact you could make genes from a microarray chip. However, when you look at his output, you see on the top middle graph that there in fact was full-length gene product that was created. But if you actually look at the product before purification, which is the lower graph in the middle, you'll see that the predominant band actually truncated products that were being created. This creates problems and issues in an industrialized process. We've evolved this technology now to have a much more predominant or pronounced effect, and what you see is Gen 9's process on the right-hand side, where there's a predominant band at the full-length product. So all of this together gives us this high throughput assembly process. And that's nice, that's effective. Now I want to come back to the demand that we see within synthetic biology. So 1 billion base pairs demand each year, And by the end of the year, we expect to have our ability, our capacity to reach about 25% of that. So we expect to be able to do 250 million base pairs per year by the end of the year, and will continue to grow. And so since the Super Bowl is coming up, I tried to think of an analogy that's comparable to that. So if you think about the attendees at the Super Bowl, it's about 70,000 people. So 70,000 people that you have to track and keep track of where they're sitting, what they're eating, where they're entering, where they're parking. And so when you think of our biofab and its ability to generate 250 million base pairs, that's the equivalent of having a Super Bowl every 2 weeks. So it's a significant amount of content that is moving through our biofab. To do that, we've invested heavily last year in creating an execution system that allows to track each oligo, each base pair, as it goes through our process. So if you were to put up on the screen all the different components of our manufacturing process and track one specific construct through our process, you could see it creates some kind of spaghetti format, and it follows one path. It doesn't go through all the modules because it has a specific characteristic. It may be a specific length, it may go into a specific vector. But now imagine that Super Bowl, 70,000 different entities coming through. You start to imagine this becomes much, much more complex. And in fact, in reality, one single order can look something like this, where you have this spaghetti diagram that shows all the different facets that are being tracked on, possibly going back through at different stages. And so, again, not only the high throughput assembly process, but the ability, the bioinformatics that's necessary to create the infrastructure to support this is critical for reaching that demand that is required in the field. So this is the foundation for making our DNA. We have the ability to go from anywhere between 500 base pairs all the way up to 10,000 base pairs. We plan on extending that to 20,000 base pairs, 50,000 base pairs, 100,000 base pairs. And we really live and drive to the mantra that a lot of the engineers in synthetic biology use, which is design, build, test. And the idea is we want to be able to explore more design space. We want to be able to test more hypotheses. We want to learn more from the experiments that we're doing. And by having this phenomenal amount of capacity, being able to offer a large number of DNA constructs to researchers, what we're really hoping to do is evolve this thinking so that we don't think of it as consecutive models of design, build, test, design, build, test, design, build, test. But maybe we can think of them as concurrent models, where could we develop a matrix of the experiment at the beginning to actually get the result faster? Could we offer enough DNA and make it so ubiquitous that researchers don't have to think about what experiment comes next, because they can do all of the experiments at once and get that done in half the time? So I will stop right there and turn over the podium to Noah, who will continue the discussion of synthetic biology. But I want to thank you from the team at Gen 9, and we'll take questions after Noah's presentation.
Thanks to the organizers for asking me to come, and thanks also to Devin for a great overview of what's happening in synthetic biology right now. I'm going to continue that thinking by talking to you about how we're using synthetic biology to convert low-cost feedstocks into valuable chemical products. And I'm going to sort of cover three things. One is how fermentation is an efficient and green and reliable chemical manufacturing method. Second thing is what we're doing at Industrial Microbes to try to make it actually the absolute cheapest way of making products. And finally, how you can be involved in the opportunity that we're creating. So chemical engineers have been using fermentation for thousands of years to make delicious products. Food, flavorings, antibiotics, these days can all be made using fermentation. And it's actually a very reliable and robust manufacturing process with a bunch of desirable features. The fermentations operate at low temperature and pressure. They've been tried and shown to be reliable and robust. You can use the same fermentation tank often for multiple feedstocks to make a range of products. It's safe. And because it uses very low energy inputs, it tends to be have a low carbon footprint, and it's a method of green chemistry manufacturing. Inside the fermentation, there's a microbial cell which is acting as the catalyst, and it's actually pretty amazing what it can do. For example, I think one of the most incredible things is it can actually manufacture itself. Some cells can double in as little as 30 minutes, and so you can fill an entire tank with your catalyst in less than a day. And it can do that using cheap raw materials. Cells are self-regulating. All these spaghetti diagrams that you can see here are a high-level overview of the pathways that occur in every cell. This is just central metabolism drawn out at a high level. And the cell has the ability to regulate the flow of mass and energy through that network. And it comes with what I think of as kind of like a built-in operating system of hundreds of chemical reactions. Kind of the way you buy a PC, it comes with Windows preloaded. You're going to work in a microbial cell, it comes with all these chemical reactions already built in. A more detailed image is so small you probably can't even see all the individual reactions. But these are the reactions that are in every one of your cells and make all of us tick. And enzymes are pretty amazing catalysts. They often have stereochemical selectivity. You can string a bunch of them together in coupled reactions. The cell can make its own energy from those chemical bonds as it's breaking them up from the feedstock. It's genetically programmable, and once you've programmed your catalyst, you can put it in the freezer and keep it there pretty much forever. And finally, we can use directed evolution, which is a very powerful method that I've personally spent the last 5 or 6 years helping to develop, which is a method of improving or changing the activity and the selectivity of your catalyst. You can broaden or narrow the substrate and product ranges and adjust the properties of your catalyst as you need. In the last decade or so, several companies and academic labs have demonstrated at both lab and commercial scale that a huge range of chemicals can be made using fermentation. And they are being used in a wide range of applications, from detergents, paints and resins, monomers and polymers for plastics, intermediate chemicals. You can make isoprene to go into rubber. You can make acrylic acid for superabsorbent polymers, pharmaceuticals, nutraceuticals, food supplements for people or animals, monomers for fibers to go into clothing or fabrics, carpets, and many more. So you might ask yourself, if this is possible and the technology is so well developed, are all of our products right now coming from this technology? And the answer is mostly not. And the reason is that the cost of production is still too high. And that's pretty much where the industrial microbe story started. A few years ago, Elizabeth, Derek, and I were working at a leading synthetic biology company to make a couple of these chemical products, for example, detergents, using fermentation of engineered bacteria. And we took that project pretty much from its inception up to commercially relevant yield, productivity, and tighter targets that we had set for ourselves. And the company that we were working for said, "That's great, terrific work, now we're putting that back in the freezer." Which was so disappointing. Why did that happen? It happened because the economics didn't work out. Primarily because the cost of the feedstock turned out to be much higher than they had anticipated. There were rises in the cost of sugar that made the project not economical anymore. So after we left that company, we said, okay, well, how can we address this problem, which is common to all of the companies that are trying to make all those other products using fermentation? We realized that the main problem was this cost of sugar and the cost structure. So we looked around and said, what is the cheapest carbon atom that you can buy that can be used for this type of process? And the answer turned out to be natural gas. Natural gas is the least expensive feedstock you can use for chemical production right now. I'm sure everybody's thinking, okay, oil is $30 a barrel, but it turns out on a carbon by carbon atom basis, natural gas costs you probably about $12 a barrel equivalent. Okay, so it's super cheap. And we're working on developing a platform technology which will be microbial catalysts that can convert natural gas into many of the same chemicals I showed you before. So how are we doing that? it turns out that nature has kind of already solved this problem. There are naturally occurring exotic bacteria that can use methane as the only source of carbon and energy. These natural methanotrophs have the enzymes and pathways that we need to be able to do the chemistry in our microbial cell factory. So what we're working on doing is transferring those genes from those exotic bacteria into the cells that everybody's really familiar with and comfortable using, the yeasts and bacterial cells that companies have been engineering for years. And that's sort of where our story and Gen 9's story come together. Because about a year ago, we proposed this project to them, and we said, this is a very challenging thing that we're trying to do. We need to test a lot of enzymes and pathways to figure out which ones are going to work. And we were awarded their G Prize last year as the startup in a competition for various startups, which enabled us to use 500,000 base pairs of DNA to try hundreds of different enzymes. And to put that in a little bit of context, this was not possible a few years ago. The cost of doing that would have been prohibitively large, but the new technologies that Devin has described has made it actually a very realistic goal for a company such as ours to be able to test so many new ideas. And what we've seen already is there are dramatic differences that you could not have predicted just by, a priori looking at these on paper. So I just want to put some more of this into some historical context. About 10 years ago, there was a big wave of companies getting excited about doing green biofuels. Many of you probably were aware of how this story went. The industry really took its lumps because in the end, what bit everybody was the failure to consider some of the techno-economics and to really do a sensitivity analysis to the fact that the cost of the sugar was going to be something that was a major part of the cost structure. But something good came out of that, and that was that we learned how to manipulate cells as microbial cell factories. The industry responded by shifting to higher value chemicals. If your feedstock is expensive and you can't afford to make fuels, everybody shifted to making higher value chemicals. And that wave is still kind of going on right now, and companies have been successful at commercializing some of those products. And in the course of that wave, what we learned was how to automate the engineering and the research and development, and especially how to conduct scale-up activities to commercial scale. And right now, we're, I think, at the beginning edge of really a third wave, which is just kind of like a tidal wave of different applications. And it's being spurred on by the fact that all of the tools that we need to go through the design, build, and test cycle that Devin was describing a few minutes ago, all of those tools are getting cheaper and easier to use, fueled by the lower cost of DNA sequencing, which is dropping faster than Moore's law, the lower cost of DNA synthesis, which is dropping faster than Moore's law, improved software tools, improved robotic tools, and a range of service providers offering, a bunch of inexpensive outsourcing options. So a company like ours, we only have, 4 people. We don't have a ton of money. We just started a couple of years ago, but we're able to basically operate out of a garage-style lab and do stuff that a few years ago you couldn't have even imagined. And so what I'd sort of like you to take away from this is that, we took our lumps 10 years ago, but we've learned a lot of those lessons, and those are being incorporated. And what I think you'll see in the next few years is the fruits of that investment are going to start paying off. I think we've learned to pay attention to things like techno-economics and sensitivity. So the last thing I'd like to leave you with is, we're right now really focused on trying to get natural gas to fuel the yeast and bacteria that everybody likes to engineer. And to be honest, we're a little bit agnostic about what molecules we're going to make from this process. So I would really love to hear from you folks in the chemicals industry about what would be the most exciting things that you'd like to see us make. And in fact, it's an opportunity for collaboration because right now we are already funded from the NSF and EPA and CCEMC and Y Combinator and some private investors. So we can actually probably work on your molecule for free. So if you're interested, I'd love to talk to you more about some of those opportunities, and happy to take any questions and stop there, and thanks very much for your attention.